So let's illustrate this a little bit better. So to keep it simple, let's take a rather simple function, y is equal to x cubed, right? And let's take a few different values of this. So for x and y. So for x is equal to 1, we have y is equal to 1. For x is equal to 2, we have y is equal to 8. For x is 3, we have y is 27. For x is 4, we have y is 64, and 5, 125. So this is just a fairly standard cubic function. And now what we're going to do is we're going to take the value of the rank. So what does the rank of x look like? When x is 1, the rank of x is actually 5 because that's the lowest value. And we see the rank go down 5, 4, 3, 2, 1. And what about the rank of y? We know that x cubed always, like, it's a constantly increasing value. So this is going to have the same values of rank as well. So 5, 4, 3, 2, and 1. So let's plot these individually. Let's take on the left side over here x and y. And on the right side over here, we will take rank of x and rank of y. This is going to be our Pearson. This is going to be our Spearman. So what are we going to do? Let's plot them, right? And when we plot them, we see we have 1, 1, 2, 8, 3, 27, 4, 64, 5, 125, something like that. This is not, let me stretch it out a little bit. So we're going to have, okay, so we're going to have 1, 1, 2, 8, 327, 464, and 5, 125. So like a neat little cubic pattern. And over here, we are going to have something that looks very different. We're going to have 1, 1, but then we're going to have 2, 2, 3, 3, 4, 4, and 5, 5. So right off the bat, we notice that this, for these values, it is close to linear. It can be approximated by linear, but each of those points is going to lie fairly off of the line. So you're going to get a line that goes through these points that looks maybe something like this, potentially, with none of the points exactly quite sitting on the line. But in the second case, we're going to have a line that very neatly goes through all of the points that we're talking about. And that line, of course, is going to be y is equal to x, or rather rank y is equal to rank x, just to avoid confusion. So in this case, we get a line that perfectly fits all the points on it. So we actually notice that the Spearman coefficient in this case is just going to be 1. Whereas in the Pearson case, it is not going to be exactly 1 because none of the points quite sits on the line. So this illustrates a pretty important difference between the Pearson and Spearman coefficient, and we will kind of look through that a little bit more as we continue with these with this slide. So this is basically the example we just looked at. We take y is equal to x cubed. We calculate the ranks, and we see that the ranks are actually all the same for these points because as x increases, y strictly increases in this function. The Pearson coefficient, don't have to go about the pain of calculating it right now, but we do know that if we plug it into the formula, and the formula being sigma xi minus mu x, yi minus mu y, divided by n minus 1, this is over I, and this whole thing divided by sigma x, sigma y. If we do that, that is going to give us a value that is 0.94. As we increase the number of points in x, like if we were to get higher values of x, we would not expect this coefficient to quite be so high. The reason it's so high right now is because we only have 5 points in x, but as it goes on, the value of y being x cubed would increase quite significantly, and so we cannot expect a high covariance, a high Pearson coefficient value. And as we mentioned in the previous slide, the Spearman's coefficient is just going to be 1 because the rank of x and y is very different. Is actually, I meant the rank is exactly the same. So the Spearman's coefficient is going to be very different. Take another really quick example and see whether that same thing holds. So let's just take y is equal to x squared. And for y is equal to x squared, let's assume that we have x and y, and x is going to be -2, 4, -1, 1, 0, 0, 1, 1, 2, 4. So we're going to get something that looks a little bit like this. So we're going to see, sorry, this is 0. So we're going to see something that looks quite like this, right? And I mean, if you take the points over here, you take this point, this point, this point, this point, and this point, we actually get, we're going to see, just given the way this is, we're going to see there's no, we're going to see a coefficient value of 0 because there's no real linear relationship between the points in this case. However, if we were to take the Spearman coefficient, are we going to see a value of 1 like the previous case? The answer is going to be no. And the reason it's going to be no is because when we look at the ranks of this, so the rank over here is going to be 5, 4, 3, 2, 1. But for y, it's actually going to be similar. So these two are going to have the same rank. Let's call it 5 and 5. These are going to have the same rank, so 3 and 3, and then 1. So what our rank of y versus rank of x is going to look like is it's actually going to look like we're going to have a point at 1, 5. Then we're going to have a point at 2, 3. We're going to have a point at 3, 1. And then we're going to have 4, 3. And then we're going to have 5, 5. So again, we're going to get a set of points that is not monotonically increasing with each other. So we're going to get a coefficient that I would guess by looking at this is 0, but that depends on the number of points that we have. So what we're going to have is basically a Spearman coefficient that is not equal to 1. Let me just write this one. And Spearman. Okay.